Hello and welcome to our fourth lecture on the lecture series, Introduction to Finite Element Methods. And thank you for your time. I can see we are already about 72. So the class is well. Now I was monitoring on my phone, so I need to mute it now. And so far so good. I think we have been going well. So each day we are learning new things. So today I was learning how to schedule a live stream so that we do not have the lag, the one that usually starts at the beginning as I wait for you to join. So as you can see, you could have joined in time and then you just need to wait. So thank you. Tell the others, tell your friends who might not be moved to this platform from the Kenneth platform to do so. So, and maybe for those who will be watching later on, I'm giving the instructions because this is a live lecture going on. It's a course in civil engineering, undergraduate student for there. So that's why we are moving as a class, but welcome, even if you're not part of our class. I believe in disseminating knowledge to the world. So I hope that this lecture helps you even to build your confidence in matters finite element methods. It's an introductory course. We have covered 3 lectures so far, so you can look at them later on. And if you have any question, just leave it in the comment section. And later on, when I get time, I can get back to you. So we've looked at different elements. We've looked at the spring element. Then we saw we could have other type of element, the bar element, the beam element, the frame. We could go to 2D element and also the solid element or the 3D element. And last week we started on the bar element, and we talked of it, or we considered it as a 1D element because we are only considering the formation in one direction. So today we are extending on that, building on the same, and we are looking at when the bar is oriented in not just in 1D. So we are talking of in a plane, like in a Cartesian plane. We could also consider, this is general, now this is just like an extension. We could also extend into the third dimension. So we could have bar element in the 3D space. Like when we have the truss, when you can, the space truss, the bridge girder, like a steel frame. So you have the third dimension, which is the depth. But for today, and for this course, we just want to concentrate on the 2D, so that now we consider the aspect of the height. We are concerned with the length, and we are just taking an element oriented in that global direction, global axis. So in our case, the coordinate system, we are saying the direction X was the same for local and global coordinate. I didn't mention about the global and local coordinate system in the introduction lecture 1, but now today we are going to see it in application. So get ready with your pen, with your writing material. We're going to have a bit of calculations. But again, I'm glad that this is not the first time that you are in this class. So you already have the basics, you already have the concepts. So we are going to move slightly faster so that you can cover more materials. All right, that being said, I'm just buying time so that I can see my student cover, move on to this area. I usually don't like leaving anybody behind, so that when I'm explaining concept, I'll not be repeating so much. So remember, this is a class. So in class, we try to explain slowly and repeating steps. So this video, even as you watch it later, might not be the same as the video that we prepare and edit, because this is raw. There is a lot of repeating explanation. Okay. So just note that. That's why actually we edit having it being a lengthy, slightly lengthy talk. All right. So I have projected what I plan to give you today. And today we look at bars in, remember the title of our course is Introduction to Finite Element Method. At the JQuat, we call it Theory of Structures 5. So again, I said most books you find them saying matrix analysis of structures. Today we are on lecture 4, looking at 3D or bar element in 2D space. And what we are going to do is formulate equation, finite element equation, also what we refer to as equilibrium equations, so that we can be able to see how to analyze our structure using the matrix method. So the bar, just consider last time what you had. You had this kind of a bar having two nodes, and the degree of freedom in each of the node was 1, because the deformation was, let me get my pen. So this is the first node, this is the second node. So you say node I, J, from the lower to higher node. So I is less than J. So like node 1, 2, or 2, 3, like that. Then we say the direction or deformation, we are only considering the horizontal. The load is applied axially, so it will only be compression or extension. And then this direction. So if you consider this direction in the direction X, so our analysis was only confined within that direction, one direction, X-axis. And we could be able to estimate or to calculate using the matrix method what is the deformation at the nodes, even when you have a system, a combination of different bars. So this you should have at your fingertips, like the stiffness matrix for this is given by AE over L. Then we have 1 minus 1 minus 1, 1. This counts very hardly because when you are solving this, you move very fast. I hope you have not forgotten for the spring, that for the spring is equals to K, then 1 minus 1 minus 1, 1. This for the spring element. And this K, we usually put, it's a matrix. So because in books, they write in bold, most books, but when you are now hard writing, you can't hard write, or you can't have a special hard writing where you are writing in bold, unless otherwise, I don't know. So that's why we, for a square or a rectangular matrix, we use the square brackets, and then for a vector, we use the braces. So you know that. And today we are looking at a case whereby now this bar, the same bar, if you consider it in a truss, okay, like that. So let me have a 3-member truss. So assume we are concerned with this element. So this is the first node, the second node. So this node 1, node 2, and then we call this node 3. Then this becomes our first element, and then this second, and like that. So if you are considering, if you look at this, when you break down the discretization stage, you break down your structure, you separate, you disassemble, so that later on you do the assembly. So you look at these bar, the bar element 1 and 2 and 3, all of them are oriented in different directions. And we always read the bar from the lower node to the higher node, IJ. So this, if you are concerned, if you are considering like our reference is the horizontal x-axis, so it means this angle. So we can explain the orientation of this element 1 using angle theta. So the same case for element 2, even though you might look like this could be isosceles or something like equilateral triangle, but the angles could be the same. But what you should know is the direction. So this is the x-axis. So it means the orientation of this bar from the x-axis is the same theta, but you see the negative angle if we consider the positive direction to be counterclockwise. So in this case, the orientation is different, like going up for element 1 and going down for element 2. All right, so let me just clear all those drawings. So our bar now, we are considering taking just one element from that truss, and we are considering now, consider like this is how it's oriented. So our bar is oriented at an angle theta to the horizontal. So this is the horizontal direction. Let's call that capital X. That is the axis, the coordinate. Now, because of its orientation, so it means now we cannot disregard the effect of the y coordinate, because like the method of resolution and geometry, we have to resolve the forces in vertical and horizontal direction. So in this case now, that's why we are considering the 2D space, like we are concerned now with the component because of the orientation, and we apply a load to that, let's say like a compressive load to that bar element. There will be a component in the vertical direction, a component in the horizontal direction. So let me repeat myself here. So initially, we had like a horizontal axis here. This is X, which coincided with the X direction. So this one, you can write it as a small x. This is the capital X. So that we can say our bar element, when it was horizontal initially, the axis, the x-axis in the local coordinate system, or the orientation, the horizontal orientation of the bar coincided with the global, the overall for the structure. Global incorporates the structure, like for the truss. So if we have our truss here, so we have the X, you always do the Y here, Y direction there, and the X direction. Okay. So this is the coordinate system, the global coordinate system, or the overall, which represent the structure. But when we come to this element, so this element, we are saying the horizontal orientation of this element 1. So this is the horizontal direction. So that will be small letter X. And then, of course, its vertical is orthogonal. Remember to keep the angles perpendicular. So the small y for this element 1 is in that direction. So there are a few things that we need to look at here. How do we move from the local coordinate system to the global coordinate system? Because different elements will be oriented in different directions. So the assembly, when we come to the assembly stage, we cannot just come and sum up or add the different elemental stiffness matrices. So that's why we have now to transform to a common platform, which is the global coordinate system. So in this case now, we are considering something like this. In the local coordinate system, you put something like the nodal. If for one element, for the individual element, use small letters to represent the axis XY. Global, use capital letters. Now, for the nodal displacement in the local coordinate system, we are introducing prime. You use that apostrophe, correct prime. So U prime, UI prime is the horizontal or the displacement along the axis of the member, of the bar member. That's the displacement like that in this node I. So that's the UI here shown. Same case, we assume that we can have VI at this node, the vertical displacement here. Now, why we are concerned with this, we are going to see. For an element is inconsequential because an element will only carry axial loading. But for our structure, our truss structure, the vertical component is important because now we are considering a combination of different elements. So if we apply a load there, load is applied vertically downwards. So we resolve the forces, or even if we say there is a displacement at this node, or calculate the displacement at this node, or there is a load applied here, calculate the displacement at this node or a certain node. So because of the different assembly of different members, this component, the vertical displacement becomes, the vertical and the horizontal displacement becomes of concern for at global scale. But at local scale, we are saying for a bar element, we say the assumption is that it's only carrying axial loads. So I hope that one is clear. So that's why we are using this small prime. And then when you come at the global coordinate system, you just remove those prime, those apostrophe there. Single quotation mark. So in this case, what you should now realize is that whatever you calculated in the previous lecture number 3, you just put, when we come to the global coordinate system, you are just like saying those equations you had computed or you have formulated, you just introduce them with the quote marks or with that mark, this mark here. I'm trying to get the correct one. No, this is not a tilde. Tilde is the one that we use up a wavy line here. But I know you know what it is. So when I get that word, I'm going to tell you. All right. Another thing now to note is at the local coordinate system, this is what I was explaining, this point and the table on this table here below, is that the local coordinate system, the node I, we were only concerned with the displacement along the axis. So because we are saying for an element carrying axial load, but at global coordinate system, the global coordinate system here, we are no longer concerned about just one element. We are talking of the system, the structural system. So the displacement both in the horizontal, consider this like this. Maybe because I've been using this truss supported like this, you could have, somebody may create an analogy that a truss can only be considered to be like that. You can have a truss like this, okay? Truss system, okay? If there is a load applied here, you might want to know in this node, or a load applied anywhere else, but maybe in this node, you want to know what is the nodal displacement. So because of the applied load, as this structure deforms, okay, the structure deforms, you see in this node, which was initially here, we have both horizontal displacement, which is u, and again we have this, from this node to this node, we have vertical displacement v. That's why we are saying there are 2 degrees of freedom at the global scale. But at the local scale, when we just take that one element, we know that the element is only allowed to either elongate or compress because it's carrying axial load. That's why what this one means. 1 degree of freedom at the node for the local scale, 2 degrees at the global scale. And this space I had left it so that you can be able to write what is the stiffness matrix, AE over L. Then we had 1 minus 1 minus 1, 1. This is for the single element local coordinate system. So any element for this truss, this member, as long as it's a bar element, this is its stiffness matrix. But now to be able to assemble for this structure, we need to transform this to the global coordinate system. So now here, I would like you to help me with a pen and a pencil, or help yourself, so that we are going to see this derivation. So this is our bar element here, oriented in the global coordinate system. So let me introduce the axis. This axis here, maybe I should draw a straight line. So this axis here, this is our axis, one axis there. And then we have the horizontal axis, right? So this is our arrow, this is Y, this is X. Maybe I have started with the overall, but I hope you not be lost. Again, if we had started with this, already the X-axis is indicated. For the local coordinate system, the X-axis or the X-coordinate is given and the Y-coordinate is given. Of course, remember why the Y is like this is because of course the Cartesian plane, the angle is they are orthogonal to each other, the axis. So now here I have introduced the global coordinate system. So what we want to do is we want to resolve to see the transformation. What does it take, or what do we need to do to transform the axis? Because once we transform the axis, we can be able to transform the nodal displacement from the local coordinate system, the u prime I, to ui. And we know that this axis here, this represents the vi at the global coordinate system, and this represents the ui at the global coordinate system. This here is ui prime. And of course, in this case now here, the vi prime, which we are saying at the local coordinate system might not make sense to you for now, is there. So let's consider just this node I. Node I. This is node J, or node 1 or node 2. So at the local coordinate system, when we are just considering one element, there is no vertical displacement at the node. So that's why we are saying this v prime I or v prime j does not contribute to the stretch of a bar element, stretch or deformation of a bar element, but it contributes to the deformation of a structure. All right. Now we have done that. So what we need to do here, we are going to employ the issue of similar triangles. So if this is this angle is given theta, if I make a right angle here by drawing a straight line, you make a straight line anywhere. It's not. Remember, you're not concerned with this node J. Yeah? We are considering node I. So let me just make a right angle here. I want to make this right angle here, so that I want to use similar triangles, and again the issue of right angle triangle, and then use this principle. I hope you remember it. So katoa. Okay, the sine, cos, and the tangent. So again, I can stretch this. This is theta. This angle is theta here. This angle is 90 minus theta here. I can extend this line to meet my y-axis in that point. Okay. Now, from a similar triangle, even you can use simple geometry, high school geometry. If this is 90, is this theta, this is 90 minus theta. Remember the bigger triangle here, this is a right angle. And we are saying this is 90 minus theta. This is 90. So the angle here is theta. Okay. So let me remove this. Okay. So we are left with this angle here. This is theta. So why am I concerned with this? Because I know VI, I know UI prime. We are not concerned with the J, the known J. So I know VI, the overall, the global. I know at the global coordinate system, the vertical displacement is along the y-axis, and I know the horizontal displacement along the x-axis. So I have I know VI. I know UI at the global scale. I am given at the local scale, local global coordinate system. I know UI and I know VI. So because I know these sides, why I was extending this angle is because I want to use these triangles. So I don't know these sides. I don't know this side, and I might not need them. So when I look at this angle theta, and I see this value here, this is, remember, this is a correction here. This is not a local coordinate system. At the local coordinate system, UI is given. It's along this element. This is at the global. This is at the global. This is the one at the local coordinate system. This one here. So I want to transform this UI to U prime I to UI. So you see, this is a right angle triangle. I know the adjacent, I know the hypotenuse. So what do I need to use? Cos. So cos theta, in this case, is equals to adjacent, which is equals to U prime I over hypotenuse, which is UI. So, and in that case, I'll have U prime I, because we want to see the transformation, is equals to UI cos theta. Okay, so it means to move from the local coordinate system UI, I need to multiply with the cosine of this angle. I have resolved it along the horizontal axis. So how do I resolve it to the vertical axis? So that's why I had to extend this triangle here. So that now I have this angle theta. I know now this is a right angle triangle because this one was 90. So of course this one is 90. This is a straight line. So I know what is the opposite. The opposite here is UI. The adjacent is, the hypotenuse is VI. Adjacent here is not known. So I don't need the adjacent. I need to use the hypotenuse and the opposite, which is sine. So again, we can say sine of this theta here, sine theta is equals to opposite, which is u prime I over vi. And this one gives me, so this one will give me, let me show you something we can do here. So because we already have calculated this, we already see that. So this one again, now I can move it here. So we are saying ui is equals, u prime I is equals to ui cos theta. And from here, you can see, again, when dissolved in the vertical axis, ui prime is equals to vi sine theta. So far, so good. Very simple. Now we have resolved from local coordinate system for the horizontal displacement, or the displacement, not horizontal, sorry, displacement along the axis of the element. We have we have been able to resolve this displacement along that direction. So the other thing that we need to resolve is this displacement here. Remember, at this point, it might not make sense at the element scale, but at the global scale, we know the vertical displacement for the structure is important. Why we are saying it doesn't make sense, because it doesn't contribute to the stretch of an element, because the load is only applied at the axial, along the axis of the member. So now here, again, what we need to do is we need to use this. We are utilizing this, the known values, the theta and the ui prime and the vi prime and the vi that we know and the ui that we know. So in this case, we can extend the axis, the horizontal axis in this direction. And remember now, when we extend in this direction, the signs are very important. So here you'll have negative ui. The same case, if we extend it downward, it will be negative. So now from this point, we need just to use a simple triangle, a similar triangle the way we have this on this side, and then simple geometry, we can be able to calculate or to obtain, to resolve the forces, the displacement on the vertical axis. We want to resolve in this axis. We want to resolve the vertical displacement in the local coordinate system to both vertical and horizontal in the global coordinate system, resolving forces. Now, what we do here is, again, we draw the, okay, let's see, how do we get an angle on this side? Because we are not given, here we are not given any angle. We might say we don't have any angle here. So what I can do here, let me extend this again. I said this one, you have to work it out. I hope you are working together with me. I hope you're not just watching me. I've just extended that. And then what I can do is, I can have another line here, similar triangle. If I do a line parallel, if I plot a line parallel to this, to the element, our element is oriented here. Remember, if you see that this line is parallel to this line. So if this axis, I can draw another parallel line to the x-axis of the local coordinate system here. Let me draw using a straight line. So I plot it here, touching both the y and the x-axis. It doesn't look so parallel, but I hope you understand what I mean. So you put it, maybe it's more inclined like that. Okay, so that this now is parallel to, now this one is parallel to this axis here. Okay, And the first one here, we said this one is parallel to this one. So with this, remember, this angle is 90. This angle is 90 here. Between, of course, the y and the x at the local coordinate system. This is 90. And we said this angle is theta here. And this whole of this angle is 90. So this angle is 90 minus theta. And if this one is 90, then this means this is theta. So this angle here is theta. And now our work have simplified because this is a right angle. This is right angle here. Let me use a highlighter. Now this is right angle here. Then this meaning this angle is 90 minus theta. And therefore this angle is equals to theta. Okay, this angle here is equals to theta. So you see, we have utilized the geometry you learned, and then we are just getting the different angles so that we can be able to resolve our forces, our displacement, nodal displacement. So if you now with this triangle, without even doing much, you can resolve, like we want to resolve this now, v prime I in this, in the horizontal axis. So we know we have this angle, theta, and we have this is right angled here. So we have the opposite, which is v prime I, and we have the hypotenuse, negative u prime, no, ui. So you use sine. So you say sine theta in this case will be equals to v prime I over minus u I. The same case, if we want, okay, now here you can see we have resolved this v prime I in the global coordinate system, the horizontal. We have gotten the horizontal component. Same case now, to get the vertical component, we have this angle. This is right angle triangle. We know this value. This is what we want to resolve. We know this is vi. So we have the adjacent. We have the hypotenuse. So we use cos. So cos theta will be equals to v prime I over vi. So in short now here we can, so okay, let me just write here without erasing that. So here we can have now, use a thicker line. So if we make v prime I, so here we have v prime I to be equals to, that's too thick. V prime I, remember this is prime, v prime I will be equals to vi cos theta. And from this one, we have v prime I will be equals to minus ui sine theta. I hope we are together up to that point. I hope you have not lost anybody. So we have utilized the causes, we have utilized the sines. So let me just move them back here. Let me move this one back here. So with the VIs, let me rewrite them here. The V prime I, I'm just transferring this one here. So this will be VI cos theta. Now the V prime I again is equals to minus UI sine theta. So in overall, we can use this. Let me use this space. So the resolution or resolving U prime I to global coordinate system is a combination of these two. Ui cos theta plus Vi sin theta. And the same, the V prime I is a combination of, so V prime I will be equals to Vi cos theta plus or minus, this will be minus Ui sin theta. So this is what you have in your note. So you don't have this derivation. And I hope you can be able to follow it the way we have derived simply. So now you can now go ahead, start writing this in matrix form. If you write this in matrix form, you'll have Ui, U prime I, V prime I. This is a vector of nodal coordinate, the coordinate system. So this will be, so you can put Ui here at the end. Ui in the global coordinate system, Vi. This is a vector, was vector. Now this one will be cos theta, sin theta. Now remember, this is V, this is U, so you need to interchange so that the Ui and Ui becomes fast, and therefore you have sin theta, negative sin theta, cos theta. And this is now how you transform the nodal coordinate system from the rock coordinate system, the nodal coordinate from the rock coordinate system to global coordinate system by pre-multiplying with this transformation matrix. This transformation matrix for a single node, remember it's node I. So for a single node, we are saying capital T. For a single node, we use that with the line there, or the tilde mark, so that we denote that is, this is the matrix. This is a transformation matrix for a single, at a single node, node I, or one node. So you can do the same for node J here. Nothing changes, just transform. You just shift these angles there, the triangles, and then you do all that stuff. So sometimes you may find, like in many books or many lectures, you're just given what is the transformation. But I feel as engineers and of course as scientists, and because you have covered this, I like the derivation part of it, so that you know where we are coming from. You can be able to relate, to have a feel of where did these figures come from basic principles, so that you can appreciate the workings. So this is the transformation matrix for the nodal single node. We use a tilde there, and then so here we can write in compressed format. You say this is U at the local coordinate system. So U prime there, and then here V, U at the global coordinate system. This is a prime here. So this is the equation for transformation. To transform from a Rocco, you pre-multiply with the transformation matrix to get the global component. All right. So I want you to digest that, because I'm going to the next slide and this information is going. So you can take a screenshot if you, oh, no, you can still come back to this video later on. So let's now move here. So the transformation. So, right, before I move from this, we said for a single node, we have seen for a single node, the transformation matrix is equals to, this is cos, sine, minus sine, cos. And these cosines and sines, these are what we call directional cosines. Now I know some of you now are already wondering. We have gone back to, is it calculus 4? Directional cosines. Okay. And sometimes they are written in short form. You may find that you can write in cos, or they are abbreviated as L for cos and M for sine in some books. I also like to say, instead of writing cos, I just like C, and sine it just like S. Now with this, for this single node, now we want to see for the overall node. So this one will be the same even for node J. So UI, that UJ, the transformation matrix is the same. To get the overall transformation matrix for one element, so we do like this, or we have something like this. This is UI. Remember this was UI, VI, UJ, VJ. We have introduced something here. This is what I was saying. You can use a pencil there to demarcate. Okay, so that we are going to fill these cells. We are going to fill the cells like that. UI, VI, UJ, VJ. And for the two nodes, remember the node one, the one that we just derived was node I, and we found that U prime I, V prime J, or even without repeating this, I can just come here and write U prime I, V prime J, V prime I is equals to this, and then we have UI, VI. So what does this tell you? This tells you that here we can say, of course, this is UI, and this is VI. Same case for the second node. You have UJ prime, VJ prime, being equals to the same, this matrix, the cos sine minus sine cos, then UJ, VJ, when you do that derivation. Okay. So, and then this will be UJ, VJ. So to fill these cells for the overall, for one element, we want to get what is the transformation matrix for a whole element, for a two node element, bar element. So you just need to superimpose UI, UI. You come here, you have UI, UI, this element. But when you come here, you have, this is UJ. So this one relates J, this one relates I. So by just observation, you can see that the two are not connected. They are not related because they are not at the same node. Okay, it's not the same node. So you see where we have UI, this one you can fill directly. UI, UI we have is a cos. VI or VI, UI is a sine. So we, is it? Yes, 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 yes. So the I's are related by themselves, UI, UI, and the VI, so is this one. But we know there's no relation between J and I. They are not integrated, so this one becomes zeros. Same case, I's and J's have no relationship, so this one 0, 0. And finally, JJ, UJ, VJ, UJ, VJ is this one. Cos, sine, minus sine, cos. So that if you look carefully, the overall or the transformation matrix for the whole element, for the two node element, this T here, we call it capital T. And remember, for a matrix, we use this for a square matrix. So if you look at this, you can see similarity here. There is this part, and it's the same part here. And then these ones are zeros, zeros. So this one will be composed of, that is the transformation matrix for each node, T, 0. Okay, we no need to, because we are already inside the matrix, no need to use this. So that will be the transformation matrix for each node T. All right. T 0 0 T, where this is the first one is transformation for node I. This is the transformation for node J. So this is the transformation matrix for the element. Not just one node now. This is for the overall element. And now if you want to, which I was giving in the next slide, if you want to now show the equation, now here I've just moved very fast. If you want to show the equation here, you just need to introduce the force vector, the nodal vector from the local coordinate system, that is u prime I, v prime I, u prime j, v prime j. Then this is the matrix, the transformation matrix, capital T. This is why I was saying this is the transformation T tilde at the nodal transformation matrix, which is the same as here. The rest is 0, 0. And then we have the nodal vector at the global coordinate system. So this is the transformation. So from the local coordinate system, you don't have to say prime, because you don't have to say I, because we are saying for any node. So that one will be u prime. To get to global coordinate system, you pre-multiply the nodes at the local global coordinate system with a transformation matrix. Now, for the whole element, we have removed the tilde, the mark that we are putting here up. We have eliminated it. So that's how we transform from local coordinate system to global coordinate system. We have been able to transform the nodal displacement. Same case if we want to transform the nodal force F prime to global coordinate system F, we just need to pre-multiply with this transformation matrix. Okay, like that. Anything from local to global, this is the transformation matrix that we use. So all quantities in the local coordinate system, be it displacement, be it forces, be it, we are going to see also the boundary condition you can be able to transform, can be transformed using the transformation matrix and these relations, which are very important. Now we have seen the transformation. Let's now move to the next stage very fast, because the other part, I think they are not very new. It's about how do we get the equation, or how do we get the stiffness matrix. So this is just a repetition of what I have just explained, that you can transform anything from local to global using the transformation matrix. And the transformation matrix for an element we have seen is a combination of the transformation from for one node and another node. All right. Same case, nodal force can be transformed. So let's see the stiffness matrix. In local coordinate system, this one you already have it in your notes in the previous lesson, lecture 3. You can watch it later, you revisit. Now, what we are doing here is just introducing the prime here. These small marks here to represent that initially what we had, we were discussing it at the local coordinate system. So this is what you derived in the previous slide, previous lecture, and you have been using. So now to transform to global coordinate system, that's our task today. So argumenting this equation, and when you talk of argumenting, which is the best word to use? Argument is like to add, make something big by adding to it. And there's a difference between argumenting and padding. Padding is you add at the edge. Argumenting you can add even at the middle, like adding extra rows, extra columns. I'm thinking something weird in my mind, and maybe ladies can confirm this. It's called body argumentation. There's those who go for argumentation. They want to increase some parts. So the same case, what we want to do here, we are going to increase or to augment our matrix. We are going to increase the size of our matrix. Why? By doing what? You know, this one we are just considering one node. UI, sorry, not one node, one direction, the U direction, the horizontal direction. So we want to incorporate the vertical direction. And this is why now we are saying you make this one bigger, you augment by adding extra rows and extra columns, so that you will have UI, VI, UJ, VJ. UI, VI, UJ, VJ. Remember, I said this, you use a pencil in faint form because they are just guides. So I'm just going to expand this stiffness matrix, which is 1, 1, minus 1, 1. The V's are zeros. This is what I'm talking about augmenting. All right. And then the last one. So this is augmentation. You expand this. We are just expanded. This is the same representation. We have just expanded this stiffness matrix here into this form. And this is what I'm giving here. So this equation, whatever you have derived before, we are saying, can be rewritten in this format so that we have introduced the component of the vertical displacement. And of course, in the force, there's no Fj. There is no Fi here. There's no force here. The forces are internal acting in the direction of the axis of the element. So that's why now here you have 0, 0 here. So this is the equation we have augmented. We have enlarged it by introducing the rows and the column representing the, for this for an element, for a single element, 2-node bar element. Moving on. This one now can be expressed in terms of, so we are saying this is the same equation again you had in the previous discussion, where stiffness matrix times the U, or we talk of F is equals to K, U. So in the local coordinate system, we are just adding this prime max. Using transformation given in equation 2 and 3, so the transformation, we say to transform, you pre-multiply. We want to transform the displacement from the local coordinate system to global coordinate system. We want to transform the forces, nodal forces, from the local coordinate system to global coordinate system. What you need to do is to pre-multiply with the transformation matrix. And that's why we are saying here, we are multiplying. Remember, we are pre-multiplying, and the order of matrices is very important. So if we say pre-multiplication, you may realize it's not the same as post-multiplication. So the order is important. So you introduce now this transformation matrix. We want to transform from, we want to to get away with the local coordinate system, local values to global values, so that we can be able to assemble our matrix for different elements oriented in different directions. So in this case, we just pre-multiply the displacement. So we said, if you can just go slightly backward. Yeah, this equation here. We say this equation. We are using this equation, equation 2 and 3. So in the coordinate system, U prime, or the displacement, is just pre-multiplication of the displacement, the global scale with the transformation matrix. So that's what we are doing in this slide here. So we are pre-multiplying like that. And then what you just need to do is to work out this. To work out this, so if you pre-multiply both sides by T transpose, why? We are trying to be left with the stiffness matrix. So we want to be left with, stiffness matrix K's on one side. So we want to move everything on the other side. So what we are saying here is you pre-multiply this stiffness matrix. If you get its transpose, and somebody can tell me what is a transpose. Okay, Humphreys Moray, please repeat what L and M is. Somebody have. Oh, yeah. Thank you. I can see people are out in class. Franklin, you have said the prime is for local axis. Yes. The prime is for local axis. We corrected that. Then Moray is saying, repeat what LMN is. And I can see Christian, you have answered him. L is cos and M is sine. Good. So keep posting them there so we continue having our discussion. All right. What is this now? Yes. We are at this stage. So I was looking at this matrix here. If you get the transpose of this matrix, the transpose, T transpose, you multiply by T, you're going to get an identity matrix. Identity matrix is like 1, whereby only the main diagonal have got one element 1, everything else is 0. So multiplying any matrix is an identity matrix. Both pre-multiplying or post-multiplying is like multiplying by 1. Okay. So that's why we want to be left with 1 on one side, only like K's, and then we can be able to know what is the stiffness matrix at the global scale. Okay, we argumented that. So we are solving this equation. This equation here is the equation we are solving. And if you pre-multiply both sides with T transpose, and you notice that this, you can work this out, you'll find it will be, I have already told you what is an identity matrix. Transposition, I know you already know. If you don't know, I don't know what to say, because I told you, you need to refresh algebra. Right? Yeah, transpose is very simple. You just rearrange rows and rows, column column members become rows and rows become column. Then you multiply one another, you are going to get identity. So that on this side, we are going to have F. Yeah, because on this, we had T. So we pre-multiply T transpose times T, and then you do the same to both sides, you are going to be left with F. And if you look at this, we talk of F is equals to Ku. U is seen here. So whatever else is T transpose K prime T is the K for the global consistent system, right? Very easy, because we are saying this is K, this is U at the global coordinate system, this is the F at the global coordinate system. So this is the K at the global coordinate system is composed of all this, which will become a 4x4 symmetric matrix. So you can work this out because already you have what is T, what is K at the raw coordinate system, and what is the transpose. So you have gotten what is the elemental stiffness matrix in the global coordinate system. Elemental stiffness matrix in the global coordinate. So it's not for all elements, for a structure. One element in global coordinate system. So we can be able to express the elemental stiffness matrix for a single element in global coordinate system, so that all of them are in global coordinate system. We can be able to assemble using this expression. And that being said, I have just realized that you have this part of the note, so I should not be moving that slowly. You need to work that out. Just pre-multiplying T transpose K, then K prime times T, you're going to get this equation. And for that person who was asking what is L and M, again, we have used it here. L is cos, M is sine. Theta, the angle theta here is given. You can see it is the inclination of the element from the horizontal global coordinate system. So this is a stiffness matrix in the global coordinate system for a 2-node bar element oriented in space, 2D space. Again, elemental stresses. This is easy. Elemental stresses, why we are mentioning this is Because once you get the step, I don't know, 7 or 8, once you get the nodal displacement or unknowns, you need to recovery stage. You need to now get what are the stresses. Because remember, the good thing is that for you to do design, you have to pass through analysis. And that's why I like structural analysis so much. Because if you understand the analysis, then from the point of that when you are starting design, the quantity, the values that you're going to use as the moment or as the shear that you're going to use as the input, you already know where they are coming from. So when you use Procon or use Stad Pro or use ETABS, the calculation you find those sheets which are so much sometimes overwhelming, it's just these calculations of sometimes if it's following the finite element method is calculation of matrices and giving out this kind of results. So that now you get what are the nodal displacement, what are the forces, you want to get what are the stresses in the member. And from the stresses, you can be able to design member section. You want to know what is the suitable cross section. If you are designing a truss or you want to construct a truss made of circular or rectangular hollow section or angle section, with the stresses now you can go to the table of sections and then you can be able to check one section whether the permissible stress, if it's TIBA, for example, permissible stress versus the actual stress that you have calculated. That's why this stage is important. And you remember, we computed or we worked out something concerning the strain displacement matrix. We found out how you derive it, and here is again another simplification. So you can look at it again here to see how this one has simplified this form, or in a simplified manner, the stress is given as this. And just to give you a small hint, it's not that it's complicated, it's quite easy. Indeed, it is very easy, because what you need to remember is for individual node, for one node, for example, here, we said, is it still in the, yeah. So you said UI or VI line, okay, is equals to cos minus sine, no, cos sine minus sine, cos, then UI VR. Okay. So UI UJ. For the stresses, of course, the VI, the V is inconsequential because the stresses in the member, the bar element, we are talking of the stress or the strength, get the area, we're talking of the cross section. So we are concerned with the direction U for the individual member. So look at this again and refresh yourself with the strain displacement matrix, and then you are going to see how we are able to obtain this part, and this part reduces to this part. All right. I think I've talked enough. I've talked for 1 hour. 1 hour non-stop talking. That's Chinese would have told me wara too much. So I want to see what the guys are saying here. Why has F changed to F when we substitute T prime with TU in the equation K is equals to FU? Let me see whether I can project that. What I'm thinking you're asking, Humphreys, is this. If I'm not wrong, you're asking this part. Why has F prime changed to F? Because we are using, you see, this expression. This expression is one that changes F prime. Because we said all other, the nodal displacement, nodal forces, anything from local to global, you can transform by pre-multiplying the values at the global coordinate system with a transformation matrix. So if you pre-multiply, if you we are doing away with the rock coordinate system. We want to use the global coordinate system. So you see, we are multiplying by t. Same case with f. And that's why here, f here, if you're asking this part here, the f, you are using equation 2 and 3 in the previous slide, so that our f now is not prime. This prime is not, because f is equals to t, f prime is equals to tf, and this u is equals to this value. Okay? I hope you understand that. All right. Then, okay, I think that's okay. So we have obtained that, we have obtained the stresses. I want us to look at a simple example. Yeah, I want us to look at this example here. Very simple, just application of what we have looked at. And I believe you are going to see application part is easy. If I just came and gave you the equation, solving is very, very easy. But when you have gone through the derivation, I think it's good as a scientist and as an engineer. Even though we are applied scientists, it's good to know where things are coming from. Right. Now, you are given a simple plane, very simple, 2 member. It's made of 2 bars with the same material properties and geometry, and it's loaded at node 2. So there is this is the node 2 here, and you can see there is horizontally P1 and vertically P2. You see the angle 45, 45. Remember 1, 2. Okay, good. I'm glad, Humphreys, you have gotten it. So you are required to find the displacement at node 2 and stresses in each bar. Okay. So easy, and very simple. What you need to do is get the stiffness matrix for this element, at the global coordinate system, because they are not inclined in the same direction. They are not oriented in the same direction, and then you assemble the matrix. And this is very easy because we already know what is K. Okay. At the global coordinate system, the K per element is equals to T transpose K at the global coordinate system, which you already know, EA over L, 1 minus 1 minus 1, 1. And then T. Or what I'm just giving you is what is in your note on page, no, not page 54. Yeah, this is what I'm repeating here. I'm indicating this. I'm indicating this. And in explicit form, this is the equation you are going to use. So you just need to know the orientation of each element, and then you substitute. You get what is cos squared, what is cos sine squared, blah, 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 like that. So in this case now, you need to know what is the orientation, and then you get the direction of cosines. Okay, here we have simplified so that you don't work with decimals. We have used the issue of special triangles. I hope you know the special triangles. There is the right angle triangle. You know that. We have the equilateral triangle. And we have the isosceles. So we say, like, if this is, if you put one here, you make it like a one. So for isosceles triangle, if you say this is 2, and the whole direction here is 2, so this will be 1, 1, because isosceles have got all equal same. So you can be able to get what is this part. Because this is 16, this is 90. So where you express as the cos of 45, like this one covers 45. This is usually 45. Then this is 45. And then this is 60. This is equilateral triangle. This is 30. And then this is 60. I know you know about these special triangles. So that now for 45, this is 1, 1. Of course, this is the square root of 2 using Pythagoras theorem. And this one using Pythagoras theorem, this is 2, 1. This will be root 2. Is it? Will it be root 2? I don't want to lie to you. Let me calculate this. This is 1, 1. So this will be I hope I'm okay. Yeah, 1. Yeah, the first one is root 2, and then the other one for the triangle would be 2 squared plus this would be 2 squared minus 1 squared, the root. This one would be root 3. I was refreshing my memories. This is root 3. Okay, so we are just using the special triangle. You don't have to use them. You can use your calculator, but you'll be punching the calculator too much with so many decimals sometimes. So cos, of course, now cos 45 is why root 2 over 2? Maybe we may need to confirm this. Cos is adjacent of hypotenuse. Okay. Yeah, because cos is equals to cos 45 would be 1 over root 2. And then what you do here, what did you use to do? Algebra. Now I'm trying to remember the work I studied first year. I was in first year algebra science. This was 2006, 2004. Oh, rationalize. You rationalize. So you multiply by root 2. You multiply by root 2. That's why we are getting the cos of 45 is root 2 over 2. And the sign. All right. You can use this, or you can just work out the normal way using a calculator by getting what is cos 45, what is sin 45. So with that, now you just come in the equation. You get this expression. Remember the cos squared, cos sine, cos sine, sine squared. You substitute what is the cos, the sine, all that. And then EA over L. And the L is given. So you are going to be left with, of course, these 2 comes because of this value here. You move it out. Yeah, rationalize. Thank you, Frank. So this is, now you have gotten what is the matrix or the stiffness matrix for element 1. Same case with element 2. So it's only a matter of angles which will be changing and maybe the value of L. But in our case here, the bar have got the same length. So the same case. Now angle, remember we are talking of angle from the horizontal global coordinate system. That's the horizontal arc. So when we are talking of this one, we are talking from the orientation, we are talking from that direction. When we talk of this node, okay, we only have 2 elements. So always know that we are talking of that direction, or they are measured from this direction. So like element 1, and then we consider for our case, remember what you call the cast. And then when you are measuring the angles, we move counterclockwise. So here in this case now, this is positive 45. I mean, this is angle 45. And then this element 2, we could say negative 45 or positive 135. I think both will give you the same value of sine and cosine. So remember the angles are we always measure them counterclockwise as the positive direction from the horizontal x-axis. And with that, you can be able to get what is the value of the stiffness for element 2, stiffness matrix for element 2. So you have K1 and K2 at the global coordinate system. So you can assemble them. And assembly is easy, just the way we did the others. We just assemble. So use the superposition principle. I told you it's comes in handy. It's very easy to apply. Superposition principle, you just need to get U1, U2, U1, V1, U2, V2, and then you start fitting in the values. And then once you introduce the force vector, or this the displacement vector and the force vector, you have your global finite element equation for the whole structure. You see now the matrices have started becoming big. Are only talking of 2-bar truss. So it's a 6x6 matrix. Now to solve this, there's other stage. We have done the assembly. The step, I think, was step 6. Is a determination of nodal unknowns, nodal forces, reactions, like that. And to do that, we need to know what is the boundary condition and the values of unknown. Like we are already given the forces at node 2. And because of this fixity here, you just look at the support condition, you can be able to know. These are pins joined the way we are looking at them, or hinges. That's why this truss might not stand. Okay, assuming that unless if you assume the node 2 is not pinned, it's not hinged, otherwise it can collapse. But anyway, for illustration purposes, being pinned, it means rotation is around, but no translation, or no translation. So it means the displacement in these nodes is equals to 0, 3 and 1 is equals to 0, both vertically and horizontally. And again, the forces we do not know at the node 3 and 1, and the nodal displacement at node 2 is what is unknown. Because of the applied forces, we expect that node to move. So that's what we are going to calculate. And the nodal forces, or the force applied at the node P, these are external forces, is given. So these are the boundary condition. U1, V1, and U3, V3 is equals to 0. And then F at node 2 in the X direction, and F at node 2 in the Y direction, they are given as P1 and P2, respectively. So that simplifies our work. So only what you need to do is substitute those values in this equation. And again, you condense. You remember the way we said, where you have the values of U's as zeros, you can remove those rows and columns so that you can have a condensed equation, row reduction. Because again, 6x6 matrix, if you try to think of Cramer's rules and getting the inverse of such a matrix, I don't think given whether manual calculation you finish today, the limitation, unless you work it on a board, is quite rather a tedious task. So to use the row reduction method or Gauss elimination method. So this is I'm moving faster because now this is the same as what you did in the previous slide, in the previous lecture. So our condensed equation, when we remove the row, what we are removing are the rows associated, rows and columns associated with U1, V1, U3, V3. So this U1 goes, U1 goes, V1 goes, V1 goes, U3 goes. So it's like this, and let me just illustrate for your case. U1, U1, V3, V3, U1, U1, V3, V3. So in essence, what you are left with is only that. This. Maybe you could use a different color. Note that it doesn't mean that the others we are disregarding, but this simplifying so that we can solve the first step, and then we can use the other equations to get the other unknowns. And this is what you have in the next slide, indicated here. So you can solve to obtain what is U2 and what is V2. Of course, you make them the subject of the formula. This is simple. You need to get the inverse of this simple square matrix so that you can pre-multiply and you move everything on the other side. You're going to get what is U2 and V2. Now, using equation 7, the one I gave you on equation 7 is given here. This is equation 7, the one we are using the strain displacement matrix. You can be able to obtain what are the stresses in each of the members. So using equation 7, you get what are the stresses in those members. It's a simple application. Application is very simple. Maybe the derivation is one that was eating into your time, but I hope you appreciate that. So that finished that question. I think we have one more. We can look at this. It's the same application. What you want to demonstrate in this case is the issue of, we said the good thing about finite element method is that it can handle complicated geometry, complicated boundary condition and loading condition, So now here we have an inclined boundary, which you can say it's slightly complicated, not very complicated, but slightly complicated, because you see this roller is going this direction. This roller is going this direction. So you can now imagine, and this part is, now this node here is hinged. So what we want to learn here, or what you are being tested here, is the issue of now when the geometry becomes a little bit complicated. So you're given a plane truss. So I'm just looking to see whether there's another question. Okay, I think you're okay. There's no question in the chat, so we continue so that we finish, I hope, by 12, or by 1. 1.5 hours should be enough. So you are required to determine the displacement. You are given the load, P, you are given the length, L. So if you are given the length L, you're not given any other length. So you need to use the geometry and these angles to be able to get the other lengths. You are given the area for element 1 and 2, and then you're not given for 3. So you determine the displacement and reaction forces. So the first thing that you should note here is that this orientation is very important. We have orientation, a unique orientation of this boundary, where you can put the small y, small x for this node 3. About assembling the matrix, I'm not going to repeat because you just need to use the K, the global stiffness matrix equation, where you are transposing, multiplying the transpose of the transformation matrix, then K at the row constant times T capital, so that you can be able to get what is the matrix, the stiffness matrix for each of the elements. So you just need to see the angle. You get the angle, you'll be able to get what is the stiffness matrix for each of these elements in the global coordinate system, and then you can assemble to get the equation. So I'm just going directly to show you the equation. So you need to work out that one out. So I am showing you the global finite element equation. And so far, if you have been so keen, you could have realized that stiffness matrix are symmetrical. That is, from the main diagonal, the element or the members, whatever is on this side, whatever is on this side is the same as on this side. So it's symmetrical. So we have simplified that. It removes clutter in our work. It simplifies your punching of calculator. But again, if as a student, if you make a mistake on this side, when you're working on the other side, you might realize it. So it means you should be very careful that you get the actual or the correct value on this side. So if you get the global stiffness matrix and also that you combine, you get the equation here. What I want to highlight in this example is about how do we handle this kind of boundary condition, the way they are inclined. And looking at this, looking at this is the loaded boundary condition. Remember this loaded boundary condition, you just obtain them by looking at, you look at, let me just return my orientation here. It's because that's our point of focus. So this is small I, small x. So orientation. So or what you just need to see to know is the angles, the angles and the length. So the boundary condition, then you look at the angles and the length when you are getting the stiffness. So about the boundary condition, you just look at the fixity. This is a hinged or a pinned joint. So U1, V1 is equal to 0. Here, this is aurora. So there's no displacement downward, but we can allow the movement in the horizontal. So V2 is equal to 0, U2 is not equal to 0. Now here, we just forget about it. At the global scale, we can't talk, we don't know what is U3 and what is V3. What we know is from the aurora is that U3 is unknown, U prime 3 is unknown because we can allow movement, but we know in this direction, V prime 3 is equal to 0. So we need to transpose or to transform from the local coordinate system of this boundary condition of the displacement here to the global coordinate system. So those are the boundary condition. We have U1, V1, and V2 is equal to 0. Then we have V prime 3 in the local coordinate system, in the local axis at node 3, V prime 3 is equal to 0. And of course, now the loads we are given load P. So F2, the horizontal direction, F2x, horizontal load applied in the horizontal direction at node 2 is given as P. And again, from the root of things, we know F3x. F3x. So why are we saying F3x is equal to 0? Because there is aurora support and there is no load that is applied there. So it means at the support, when there is no load applied, what we calculate is the reaction. But because of the aurora support there, we know the reaction is equal to 0. It could have been 0 on this node, but because there is a force applied here, of course there will be, we already know what force is applied at that node. But on this direction, the direction, local coordinate system at node 3, we know F3x is equal to 0 because of the aurora support. Now record this. So this is where we started today, and we derived, or we came up with a simple node where I was drawing those rectangles, similar triangles, and getting the issue using geometry to be able to get the angles. We got at a single node how we transpose using this, and this one we wrote it as T tilde. Okay. So we can transpose from the local coordinate system to global coordinate system by pre-multiplying with the transformation matrix per node, which is cos sine minus sine cos. So if you recall that, then it means we can transpose or we can transform the values that we have at node 3 to global coordinate system in this manner. So V3, so if we want to transpose V3, which we know is 0, we want to transform it into the global coordinate system. So you just need to take this, if you want this V, you just need to, what we are taking is this part and this part, okay? And that's why it's simplified here. This is minus M L, then you multiply by U3, V3. And you already gotten what is L and M at this element 3. So that at the end of it now you can get V prime 3 is equals to, can be expressed using U3 and V3 in global coordinate system, okay, which is equals to 0. And further working or simplifying this equation, we see that U3 minus V3 is equals to 0, or U3 is equals to V3. So as like already we have been able to use the data we have from local coordinate system at this node, which had some complicated, slightly complex boundary condition, but you have been able to utilize the fact that we know one value is 0 to be able to get what are the nodal displacement at that node. All right. Now we move ahead. Similarly, at the same node, we can do the same for F. Remember, we say the transformation from the local to global, we pre-multiply. And this we are with the transformation matrix. And now we are talking at the node. So again, we pre-multiply with that to get this kind of an expression. So we are able to get what are the values of F3 from the known values at the local coordinate system. So we have been able to get at the global coordinate system. So this one helps to simplify our equation. Remember the equation, this equation. To solve this equation, to be able to solve this equation, if you have so many unknowns on this side and so many unknowns on this side, your equation might not reduce significantly. So it might be difficult to solve. So that's why we want to get as many values as possible which are unknown, so that we can factor in there and the ones which are 0, so that we can cancel those rows and reduce our equation and start solving for the nodal unknowns and nodal displacement. So we have gotten what is F3x, the expression at the node 3. So we have been able to utilize or to resolve that issue of this type of boundary condition. And this type of boundary condition, where you have boundary condition or restraints, remember boundary condition are restraints. You are restraining our structure in different directions. We talk of that being a MPC. The problem we are handling here is MPC, which is referred to as a multi-strain, multi-point constraint. Multi-point constraint. There is our structure is restrained using boundary condition in different direction or at different points. Okay, so it's a special case and we handle it. The good thing is about infinite element software, you just need to specify those multi-point constraints, and then it does the transformation for you. So with that, our work simplifies. So you just need to substitute the values of load and boundary condition in your equation, and that one will end up deleting first, second, and fourth rows. So you just look at this. Why are we deleting first, second, and fourth row? We are deleting U1, V1, and V2 because we already know U1, V1, and V2 is equals to 0. So you can delete those rows and the associated columns. So you'll be left with the simplified equation like this. So you see, this is the algebraic equation or simultaneous equation with 3 unknowns. It have simplified to a reasonable level where you can be able to handle. So we can still go ahead from the multi-point constraint. We can go ahead because we already know what is the force relation at node 3. So our equation here, we already know what are the F3x, what is F3y from the relationship here. You see, from this relation here, we can relate these two here. It will simplify our equation. So F3x and so F3y is negative F3x. And remember, the same case, U2, U3, U3, U2, U3, U3. this equation is U2, U3, V3. I was looking at this, and I wanted to take you back here. U3 is equals to V3, right? So that's why in this equation, V3 becomes U3, F3y becomes negative F3x because of this expression. So our equation simplifies like that. So you see, you only have, on this side, only U2, U3 as unknown, and on this side, you have 3x as unknown. So this one equation simplifies to that, and you can be able to now solve. So if you use this third equation, the third row here, you are able to get F3x is equals to 12, 6, 10 times 10 raised to the power 5 U3. Substituting that to the second equation, this is the second equation, so that you use U2, you get that expression. And solving, you are able to obtain the displacement U2 and U2 and V2, because U2 and U3, you're able to get them, the nodal displacement that we required. And of course, we know U3 is equals to the same as V3. Yeah? So your equation is solved. I'm moving very fast here because it's just about now working out normally. We have furthered what was the small charge that was posed to us. So now he's just moving very quickly. And now from the global finite element equation, you can be able to calculate what are the forces by just substituting what are the U3s, U2s, and the other knowns. You work it out, you'll be able to get what are the nodal forces. And that's it. So that said, and I'm happy that we've been able to cover within the time I was estimating. So I'm looking at the chat area, and I can see people are still digesting. So maybe question may come on later. So I said even after the end of this lecture, when you come back and then you have somewhere you need some explanation, for the benefit of other people. So instead of sending me an email, I had said it's okay, but if it's a question that can be written that requires clarification, you can just comment, right? Put a comment there, then we can address it and people can benefit. All right, that's the end of my presentation today, and we have come to the end of the bar element, the part that I wanted to cover. Remember, it's just an introduction. We are covering easy and introductory materials. So we want to have time to move to the other elements so that we can have a feel of at least different types of elements and how we use them in matrix analysis of structure or using finite element approaches. All right, I open now to question. Use the chat area, that's what I encourage, but I can also share somebody who wants to join me for a live question, unless if it's very necessary, if it cannot be typed. If it can be typed, is okay. But if you really need to come into play, then I don't have a problem. I can share the meeting code. But as usual, I always say don't post it publicly there. We don't want spamming. Yeah? Or you people, you don't know about being recalled. I was recalled in one Zoom meeting, and it was a religious meeting, so it was not a very good thing. Eh? So I have sent the link to the class lab groups for those who want to join me here or for a question. But if your question is simple, can be typed, just use the chat bar. So let me get those questions. That's the end of our lecture for today. Make sure that you have registered. Registering for the classes by logging into the Kenneth platform. Kenneth platform have got a system of recording the people who have come into attendance. So that's why you have to start there. And when you get there, then your name, you start with your 3 names, name, registration number, the full names, and then registration number. So I usually generate that list. I get it, and I forward to the class rep, and I hope the class rep usually shares with you so that you can be confirming your attendance. Remember, the requirement at the JQuad is that you must attend 2/3 of the classes so that you can be allowed to sit for exam. While I try as much as possible not to to penalize students on that area, but it's for your own good. Because like now we have had or covered some materials which were not there in the previous notes, the one that I sent to the other, or I was using to teach the other years. So you get new materials because we continue improving. So any question, anyone? All right. So I might now stop sharing. If you have any question later on, you are also free to ask at that time. Let me stop the share. Oh, if I stop sharing, then you're going to see my white hair. Meeting information. I didn't need Benjamin. Yes, Benjamin. So if you're going to ask us a live question, why don't you put your camera on? We see who we are talking to, if you are okay with that. Yes, Benjamin. Welcome, welcome. Let me get you a question. The book I was telling you, if somebody needs to read further. Okay, I don't know, my background sometimes, I'm using virtual background on Zoom, so maybe you cannot be able to see it. I have a good book here, Finite Element Method it's by Thomas J.R. Hodges. It's a good book, but it's slightly advanced. So for those who might be doing projects in finite element at masters and all that, it's a very good book because you run the theory. I was waiting for Frank. I saw you joined the meeting. Benjamin, the people joining here are those with questions. You have a question?
Could you please share with us the workings for the 2 examples?
All right. Share.
I mean the notes.
Okay, I have shared.
As in, for our future, because what you have is not having no workings.
No. That one I made it very clear. You know why? I did this. I have taught this course from 2016. I taught it in Kigali, Rwanda. And I found that people just look at you when you are solving. They just look at you. This is calculation. This is not theory. If you don't work out this thing by yourself, how are you going to understand? You understand me? I'm doing you a favor. Because I did that, and then many people, when we come to the exam, they flop. But this one, if you solve, because it's very, very simple. One thing I know is that you can make your own notes from today's class. And when you are making those notes calculation, when you are doing that calculation, it sinks to your head. But if I just send you the worked examples, everything, yeah, I'm very sure you are just going to look at them and see them. They are very easy. So I might continue adding some working out later on, but I don't plan on giving out this. Is that okay? Martin. Actually, what you don't have is very small. It's something very small because I have given you all the notes, the derivation and all that, but the working example there, the worked example is the calculations part only that you don't have. And again, I gave you the textbooks. Have you people gotten those 2 books that I was saying, the 2 references, the first and the second? Okay. All right. So if no further question, if no one else is here, and there's nothing in the chat, so just like to say thank you. Thank you for attending. And just a small announcement. I thought it's interesting. You're going to do your research in failure, but if by second semester you can start thinking of a topic, I would advise you so that by the time you reach failure, you already have an area that you want to research on. That's an advice. Number two is that we are in the 4th week. So according to the university schedule, 5th or 6th week, we should be having our first CAT. So let's agree with your class rep. I want you to try one of our Monday classes, because according to my schedule, according to the timetable, we have Monday tutorials with you. So instead of you using a Wednesday, I'm planning on using a Monday. And today is what? Today is 9th. So next Monday will be 14th. So discuss amongst yourself, and then let the class rep inform me which Monday is okay and what time, whether it's 21st, 28th, but let's not go past this month. So between next week, 14, 21, 28, select one Monday and let me know the time. Of course, the CAT will be physical. We are going to use one of the rooms there, the big rooms. And it will be a short CAT just for fulfilling the requirement. My exams usually are very easy because I believe in people understanding. But if you look at the worked examples and you don't take a pen, it might be complicated. All right, that's all for today. One guy have got the book you have just shown. So what you are saying, you are requesting them after the class. The worked examples. No, because if somebody knows, okay, what is so difficult in getting this? We have gone through it, and then getting the calculation. What's so difficult? Why do you want me to work it out again for you? Why do you want to grow lazy? Because that's what you are advocating for. Like now, we said getting a stiffness matrix. And I just jumped. Even in my notes, the one I'm going to give you, if I give you, the notes themselves don't have that part because I have jumped it. I have not prepared that part. Okay. And again, my working, I'm preparing using those two books also. And also, okay, sometimes you get materials from other literature, especially journal and latest literature. But you can get those two books, some very good examples there. Okay. So if I'm going to give you the worked calculation, I want to see your worked calculation. That will be the assignment. I want to see what you have worked, where you have stuck, I give you. Otherwise, I won't, and I'm helping you because I've seen from experience people blathering. Maybe I'll give you during revision time towards the end of the exam. So that you have your note now, but it's not a promise. Okay, that's all. Let's meet next week. Class rep, please inform me when you want us to have our first CAT. So I'm going to end now this live streaming. Bye-bye.